We're catching up on talking about inverse, for the moment, latent inverse dynamic models. The last time we got as far, just to remind everybody, there are models that can be made these days, even actually from a few years ago, that would do some like text to video generation. That's like some of the first ones from those are even from a few years ago, from back in 2021. But now these models, they could potentially be used for the types of world models that we've been talking about. So one example of this, which is a bit different because the previous ones were like put in text, get out some video of how the world or like the simulation of the world should unfold for the next few seconds. This one is going to actually try to learn more of this like latent aspect, because the concept is if there is this forward dynamics model and it's learning to unroll and be able to predict things that are happening in the future, somewhere in there it should have some understanding of the dynamics of the world. But if we like take this concept one step further, if it's like recording or like producing a video and there's a person in the background of that actual video, it means that to properly be able to produce that video of how things are unfolding, it needs a model for that person embedded somewhere inside of this forward dynamics model. I mean, to be honest, that might make us a bit concerned because this means all the complexity of a single person at least has to be embedded inside of this system. And that's not going to be an easy thing to accomplish. Human beings are all pretty complicated and dynamic and do a lot of different stuff. But for the moment, it's just capturing motion. So this model is going to kind of build on this concept a little bit, where there is some like frames that are given in for part of the model, but inside of this, the predictions into the future are going to be conditioned on this latent dynamics model. And the hope is, and this latent action model. And the idea is now there'll be more of a state is evolving and action is evolving from this. Now the outputs for this actual model can be controlled in a different way. So it's not just going to be text conditioned. Now this part of the forward dynamics model takes in a state and an action, and out of this kind of inverse dynamics model training process, there's a type of forward dynamics model that's constructed, one that can be used. Does that make sense? Pretty clear so far? There's certainly a detail or two here. So this was one of the papers, I believe, that I signed for the reading. So does anyone remember some of the details about how this action latent was actually learned? Yes.
And predetermined number of blocks, like they know how many actions they will learn before.
Yeah. That was certainly one of the things that seemed like it was a bit important here, because a lot of these videos, how many people have played platformer games before, or at least are kind of familiar? Really, the actions in these games are up, left, right, down, maybe like kick or punch. So the code book can be pretty small. It's being used inside of the VQVAE, which is also nice because then it could be controlled through a couple of keys. So there's a bit of an implicit design, at least for some of these examples that were in the paper, that they know what the action space is going to be embedded inside of this model. Then the code book that's being used for the VQVAE can be kind of tailored more towards this. It's not so bad. It can work pretty well. Does that make sense? This is a bit of a... Essentially, before being able to make this video model, and this is like a good suggestion when thinking about different types of things you want to do with these models, there should be some evidence already that what is hoped to be inside of the model does already exist. So like somewhere there is a physical controller joystick that someone has used to generate that model. And now let's just see if we can learn that control joystick inside of the actual video generation process. Short story is good not to get too far away from something that currently works, even when you use these models. And of course, the nice part is this also at least some of the experiments in the paper, and they're also applying this to some robotics experiments. So this could be trained on a bunch of robotics data. And there's also a somewhat similar action mapping in this codebook. Now it's kind of, I think it's pretty much the same, but the idea is it's describing the end effector for the arm. After this is trained, now the arm can kind of go like left, down, up, and right in the way it generates videos. You could generate sequences of control via the simulation this way. You have a question? Okay, sorry. And this is a little bit different than what we've at least talked about somewhat using inverse dynamics models. The way that they were introduced the first time is some video is given, and then problem is being able to infer the actions that make that video actually occur. This is kind of trying to bake that step into the model as well. So now that this is an inverse dynamics model, you can also control the actions that go into it. So there's a bit of this trade-off of, well, actually, maybe we can, there are different ways to use this inverse dynamics model in order to get basically what is hopefully achievable from it. Because it is a large process. Because this would otherwise have to be split into two steps, right? Where you have some video generation model, which is going to be ginormous, some inverse dynamics model, which is also going to be enormous. This work is trying to put those two together, so at least it's one model instead of two. And then in there, also try to like extract a little bit of the like forward dynamics process from the inverse dynamics process. Great. Any other questions about this?
I've seen the Genie too.
Seen, yes, but I'd use that word carefully. There's a web page for Genie 2, but there's no paper for Genie 2.
Like the video are really impressive, like 3D, and you can see the walking inside the like computers really observe that.
Mm-hmm. That's nice too. So yeah, if you're interested, you can go check out the Genie 2 webpage. There's some even more high fidelity images that it learns, or videos that it learns how to generate. And scale, actually, in this sort of area, scale is probably one of the things that becomes more and more important in terms of what can be learned inside of a Latent dynamics model. So for example, and by scale, let's think of it in this case, normally means data size. Let's also talk about image size here. So some video generation model is trained over some of these videos in the bottom right. So let's zoom into these robotics ones. And these are already a little bit pixelated. But if these particular images I was trained on, or this can here only ends up being represented by a single pixel inside of the image or less, then if a process is used to train a video generation model, do you think the model will end up picking up on the dynamics for the can? Probably. Not unless whoever's making this is some absolute magician and like hyperparameter tuning, will it end up picking up on that? So where scale also starts to matter a lot for these models is being able to increase the image size, because then it understands these are objects. They kind of implicitly end up getting a little bit more weight in the loss function rather than just what might look like noise if it's a single pixel moving around. So if people are interested in like using these models, there's some level of image fidelity that's going to be needed to generate these. And this is why these have been also like gaining more popularity a bit lately. Before this wasn't possible. People also thought video generation models would take a fair bit longer to be able to create because of the amount of compute that's needed to train them, even the people at large companies. But they do seem to, or some accessible models people can use, but not always at the fidelity that we might want, especially for robotics tasks where the details matter. And essentially this model needs to capture the dynamics of what's going on via this video, like learn all of Newton's laws via just tons of interactions and videos. Hard to detect those without more video detail. All right. That makes sense. Great. Any other questions about Genie? Comments? Who read the Genie paper versus the other papers? Okay. Yeah, it is a nice paper. It's obviously, sure, there's a paper for this one too. There's no code for this one. Otherwise, this would probably be fun to play around with and add in some more experiments. So a good concept for now to see how it works. Great. So kind of digging into this concept a little bit better for what is going on inside of this forward dynamics model while it's trained. And the process in this is it's training some sort of latent dynamics model. So this is kind of like the way we would try to explain the mathematics that could be going on in the background. Because these models are trained from images, which means there's a whole bunch of stuff that's really not captured inside of the image. In fact, for the Genie paper, one thing that they note is it's like a side-scrolling platformer game, but generating new stuff that's coming in that makes sense, which is kind of an interesting concept because it doesn't really have information about that yet besides what was in the training set. But somewhere from all of these observations, some state needs to be inferred. And this is what's actually going on in the actual background. So we did talk for a bit about like doing partially observability and handling that problem of like how much history needs to be kept in order to infer what the current state is right now. It's a very similar process, but now these video generation models have to infer what this whole like data generation process is and needs to infer what this state should be given some either text or video that's been given so far. And at least, so normally in the POMDP framework, there's some observation model for like in this state, what's the probability of seeing this actual observation? And then the actual dynamics model that is basically baked into the model. And this is what we, like, when training these video dynamics models, what we hope is basically learned inside of this and what is hopefully reusable after these models are trained that we can build on. And we didn't talk about it too much, but also some reward prediction model. We'll get into that a little bit later in today's lecture. We've kind of ignored that we also need rewards, potentially. We've just been predicting, talking about models that predict future states. So the challenge here, I mean, the challenge for a great number of things, but what these models are trying to do well is be able to predict this latent state. The better they get at that, the better they're able to operate in our more, kind of diverse and crazy world. The same thing that we also try to figure out, given like the small amount of information that everyone gets to see in this room. Although I'm guessing many of you probably have been in some form of information overload since. Does that make sense? Like this is a huge, well, this is a real challenge. It's a real one to help solve. And there's different ways to tackle this. And hopefully all of you can see this as well. That's down here at the bottom. But like one of the key points I'm trying to make here is think about how this could be learned. There's different types of signals we can talk about for being able to learn this latent state. If it was just using something like reward doesn't provide a lot of signal. And that process would still be able to have to force us to learn this latent state at some point. It's possible that, likely that using these video generation models, there's a lot more information from every pixel that it can use to try and infer this latent state. And hopefully that will help learn a better latent state model. Okay. All right, there's still a number of challenges in being able to do this. So we haven't, in terms of like, sorry, these algorithms, they're not magically undoing the problems that we run into with like the dagger proof, like how much error can accumulate and how these are being used. So even with some more error, there could be a lot of epistemic noise. So this means that the model might not be perfectly accurate. It's going to accumulate noise. It's true there's a couple of great video generation models. Most of them still only generate for a second or two. And a lot of the planning problems that we'll be concerned with and that robotics would be nice to have are going to be longer than a second or too long. So this is, again, A video generation model is another type of autoregressive model. So it has to basically learn to predict on itself after its previous frame that's predicted. So this video generation process can also accumulate error, very similar to the way behavior cloning can accumulate error. This is this autoregressive process. So here, this might have, if this is that epsilon big O of t again, this can still face some of the challenges of the longer the video that is desired to be generated, the more issues it could run into in being able to generate something that long. Not just computational ones, but in fact of it like being able to build on itself. They also need a ginormous amount of data. In this case, I mean, even in terms of robotics data, like the video data that's needed to train these models is orders of magnitude more than what we've got for robotics right now. There's probably like petabytes of data, which is an insane amount of things in order to be able to train on. So still being able to, all right, train and find this true state is far from easy, but that shouldn't stop, research from trying. And maybe I'll ask about this question, which I touched on it for a bit. So is image construction really the best way to go, since we're talking about signals? So there are other options. We could just do like classification from before and have a video that like classifies stuff that's in the image rather than having to do entire like pixel reconstruction. So which one of these seems better, or which one of these might have caveats over the other ones? Any thoughts? Maybe I'll give, go ahead.
The more information, the thing that we are reconstructing is, the better it is. Because like as you said in the etching up the dynamics with a camera, even if we are reconstructing an image, might not be enough to get the physics of the objects. So the more information we can reconstruct and somehow compute a loss over it, better it is.
Yeah, but I also want to key on this word information. And maybe I'll add a little bit to this. There's also this idea of useful information. So not that everything you said is correct, but there's one example I also like to give for like, so you can probably predict like the video process or whatever, the visuals, what you're seeing me doing for the next little bit. But there's a whole lot of stuff in the background that isn't necessarily really helpful to that, like needing to be able to model and predict over it. But when we're doing reconstruction of images, it reconstructs everything. Some of the stuff in the background could be like total noise and just pure craziness. And so does that mean, like, what are the limitations and challenges of using this occasionally? This ends up not, becoming much of a problem technically for like the Genie work, because the model that's being used is trained over a distribution. A lot of it is video games, and in there, video games are also kind of designed. If any people are a bit more familiar with art, there's like a foreground and a background. The background is just sort of like meant to be there. You're really supposed to ignore it for the most part. It's even like use different coloring, things like that. And it's that foreground stuff that's like, okay, that's where all the dynamics are probably happening, where the agent is moving around. That's where the information is. The model needs to learn how to understand. The background can just be this color, which was a terrible choice, or this color, which is, I guess, just something we're forced to live with because of the way blackboards work. But these don't really help, a lot of much for inferring with the current dynamic stuff. So that might lead some people, well, we could make the model that will predict just rewards. Then we know the data that's being predicted is truly like information only. But then we run into another problem. Does anyone have ideas what the other problem is if we're just using rewards? No? Kind of like the inverse problem of having too much information. Yeah. So now there's very, very little information. And a lot of the problems are, it's like in different states, you can receive the same reward. So there's a huge aliasing problem. Sort of like this looks like something that can be predicted. There's some signal right now, but it's really hard to figure out like what caused this actual reward. You need, again, huge amounts of data in different situations to figure out how that might work, potentially. Does that make sense? Any questions about these so far? All right. So this is where there's definitely been a couple of papers that have kind of like branched off from this. So, and we'll talk about these in a bit more detail. But instead of doing entire image or reconstruction, which is also pretty computationally huge, instead there's a couple of other models that are essentially just trying to train models, learning good latent dynamics, but they're just trying to predict rewards. The trick they also use in these is it's trained not to predict a single reward. This will either be trained to predict rewards for the next 20 steps, so that at least there's more information to understand what's going on, or some other, you can maybe predict some other things about what's going on in the world, but doing this over sequences, again, gives a bit more signal to actually be able to train the model. Yeah, these are just sort of like the lovely diagrams from a few of these papers, but basically predict k-steps into the future for all the rewards into the future of what these models are, and not doing total video generation. All right, so I'll hold off on that because we're going to talk about those in a bit. Okay, so a little bit more for like the math grounding here. One of the other limitations, because we've been talking about using these for planning. So if the agent is going to use one of these to actually construct a plan, it should at least be somewhat confident in the plan that it's constructing. But we know, again, that no model is completely perfect. So here, if the model still needs to explore, basically to improve, we don't necessarily want it to overfit areas of the state space. So by this, if the agent just assumes the model that it has is entirely perfect, uses it for planning, it's going to still potentially go to some really high rewarding spot, but it's not correctly high rewarding because the model is not correct. Sorry. So instead, what can be done, although this is really see what's used to make predictions. So some way to be able to compute the model's confidence and how good is its prediction at this particular state given this particular action. And one reason this can be nice is it can be used to either help collect data. It certainly can be used as part of the optimization. So if the agent is using this overall system to do some planning, then it can take, all right, this is a high value plan, but the confidence is really low. So the algorithm can downweight this plan according to like the growth or basically the unconfidence or the variance or non-confidence in its actual plan. They do some exploration that way. And then do this optimization using this type of expected value. And just keep in mind, this is not really a worst case bound. We can talk about it as well, but this is still a bit optimistic. But it doesn't entirely eliminate any possible worst cases. So it's not optimizing a policy. It will always guarantee to always be above this level of goodness, in terms of how it plans. But at least it can be a bit better than planning from nothing and being very, very overconfident in how the model of the world works. Yeah, and basically just using something that kind of computes expected value would be good. So this is becoming a small, growing area right now, especially for robotics. Now that there's more and more foundational models, some way to be able to get them to be able to predict something related to their confidence. It's actually something that transformers are really terrible at capturing. They still tend to get extremely overconfident in themselves. Still can lead to some, potentially bad outcomes. In this case, not everything is destroyed, but the expected value for the plan is much higher than the actual value when it's used in the task. So there's a couple of different ways to do uncertainty-based models, just to keep these in mind. For some forward dynamics model, the output for the model can actually be trained such that it'll have some confidence and some distribution over the possible outcomes. Can also be done for continuous outputs. The problem is, even if this model is trained with some prediction at the end of it to estimate the output of that actual distribution, this can still end up being fairly overconfident because it's just at the end of the model trying to predict possible outcomes. A bit of the challenge is the optimization process really needs to consider the accuracy of the model, like the parameters in the model and how well they actually fit the data. So this changes this a little bit, where we can talk about two different types of stochasticity that exist. There's the one that people are probably a bit more familiar with when it comes to machine learning. These are areas that are basically epistemic uncertainty. It's similar to just saying this problem of like the agent doesn't have enough support in some area of the state. So because there's no support, there's no data for it to understand and learn what to predict there. It essentially can't do a better job of being able to predict there. But if it's epistemic uncertainty, this means that gathering more data will help reduce that uncertainty in the model. The other part that's trickier and a bit more natural in the world is aleatoric uncertainty, which is, things that no matter how much additional data is collected, there's no way to become more certain about that process. So I think you want to give some examples of things that are aleatoric uncertainty? Anyone think about some of those in your free time?
Roll of dice, I guess. Cannot predict the value of the dice when you ask for data.
I'm just trying to think of the example right now where if I plugged your question into one of those video generation models, would it roll the dice there and be actually deterministic in the way it would roll things?
I guess. I could agree that there's emotional data.
Yeah, like the concept is mostly correct, but I guess I'm being a bit pedantic because of the details in this class since we're doing a lot of physically correct models. But if you at least had the initial conditions of that dice and a really good model for the dynamics, you could probably predict that one. But you still need like the initial conditions of the dice.
Yeah, you need the air pressure and things like that. There's too much variable to do.
Sure. Okay. Yeah. Air pressure is at least making this harder. Now we'd at least have to model the entire world very carefully to see how the air is going to change when the dice is rolled. Or if, one of your family members sticks their hand out on the table because they weren't paying much attention. Anything like that. Other examples?
If you want to go that way, like the position of like an atom, an electron.
Yeah. That's like Heisenberg's uncertainty principle. We're trying to figure out how to measure things. That's a good one. We'll go through a few more examples. Like these are important to consider, especially if we're trying to figure out that the model isn't estimating things well. We should be able to understand if it's going to be in the epistemic or aleatoric uncertainty bin, so we don't spend our time trying to figure out the locations and speeds of atoms more than we can physically measure so far. One of my other favorite ones is just the cosmic background radiation that exists in the universe. Pretty good. The one that is actually not correct is the random number generator on most of our cell phones. It's actually not even pseudo-random. It's actually really hard to generate a random number and for it to be really, really random. And some computers have like special random number generator systems to make them even more random. It's a really weird process. Also because computers have been designed to be deterministic. So keep those in mind. One that actually keeps my mind more as well is to figure out, okay, for the most part, aleatoric noise comes a lot from people. So like when robots are interacting with people occasionally, figuring out the uncapturable information there and being able to reduce that is something to keep in mind. Okay. So yeah, there's a bunch of other examples. And then, yeah, as I said, epistemic uncertainty is wherever more data will help. This is all the areas where robotics companies are currently spending most of their money, is basically reducing the epistemic uncertainty for their models, even if their models aren't actually modeling the epistemic uncertainty. Okay. So really, conceptually, one of the best ways to be able to optimize this is now the optimization needs to integrate over basically all of the possible sets of parameters for the model that would explain that like data generation process. So this isn't at the end of optimization, try to predict a little distribution over possible future states. This is also taking into consideration the model parameters in the optimization process. So instead of basically having some particular output for the model now that is some distribution over future states, instead to get that distribution over possible future states, some sampling process has to sample the parameters for the actual neural network. And then from that, compute a bunch of outputs over those different versions of the network. And then that gives the distribution. And this will give a better estimate about kind of like model uncertainty in design. All right. And then there's at least, that conceptually sounds great, trying to keep an estimate over all your parameters. But does maybe some people start to see like why this would be really, really hard when we've got really large foundational models? If now this previous system here basically needs to do some sort of like computation over all the possible parameters that some giant foundational model could possibly have. This is going to be, if this wasn't already fairly intractable and difficult to do, doing it for a foundational model is going to be almost impossible. At the moment, when these models are being trained, they're already big enough so that only one of them can even fit into memory. So there's no extra room to like sample additional versions of this model and be able to compute some confidence or something like that over how the model works. So this is definitely one of the, at least memory footprint and having to be able to compute this is one of the reasons why this hasn't really started to show up or being like used yet in some of the models that are being done or being used for robotics for sure. Hopefully we'll reach that at some point, but there's definitely some work figuring out if there is some larger foundational model, maybe there's somewhere along this foundational model to inject noise, such that maybe it's just the last few steps or layers or something like that that are good enough to help this model estimate something that's close to a good estimate for its confidence. But that's still a very tricky thing to do. Okay. But if something like that is available, it can be used to be able to do like stochastic model evaluation. The nice part is, so it's stochastic. There's not actually a whole lot here that we need to change about the algorithm in order to get this to work. Instead of running a bunch of trajectories through the forward model and planning with them, the only thing that really needs to change is now at the beginning of an episode, or kind of like at every step. What should happen is you also need to either sample the parameters for that actual network again, and then compute an output. And then you get a better, then through this sampling process, this gives a better estimate for how that model will perform. Because remember, that model is some distribution over something that currently should model the stuff in the data set well, but it's only been trained so far to be so good. Something like that. So how this often happens a bit more in practice, to be a little bit less memory, consuming a little bit less memory, is rather than doing an entire, you could make a Bayesian network that'll basically like track a mean and a standard deviation or variance over every parameter for the network. So it's kind of like a network with twice as many parameters. An often way that works a little bit better in practice is basically just to take an ensemble. So let's keep X number of copies of the network around. Each one of these copies is trained over a slightly different segment of the actual data that exists. And then when basically processing plans, start to just select members from this ensemble. And that'll give an okay job being able to actually estimate the confidence of the model. And then you can use that for some better stochastic planning. This is definitely something that people that are working on doing stuff that require any sort of safety in their planning are extremely more concerned about trying to figure out this process better and estimate uncertainty more accurately. Okay. Any questions? Good so far? Awesome. All right. So kind of getting back to this question a bit more, this is a bit more of a discussion now for how should agents use these world models. So this is kind of the UniPy versus Genie way of discussing this a bit more. Okay, so who read the UniPy paper? So we've got a few. All right, can you remind us, I guess for a bit, how like the IBM was used in UniPy?
Like they wanted to take advantage of internet stale data, so like YouTube videos where you don't have access to actions. So you just have like subsequent, or consecutive frames. So you can, if you want to label that data, you try to learn the dynamics between those consecutive frames. Versus like previous works where they had to have data sets with labels such as actions and rewards.
Mm-hmm. Yeah, and then from this, and then part of the difference between, so that's basically a description for UniPy, since we haven't talked about it. We focused on Genie a whole bunch. And in this case, like what's being used here in this IDM is a bit different. It does train this model that can basically figure out how to predict some videos. But from in the paper, like they do end up having to use a different model to end up coming up with the actions later. Tremendous. Because remember, Genie was doing this as like one group. Okay, there was an inverse dynamics model being learned and some understanding for how to actually be able to use the actions in this kind of weird latent action dynamics blob that was inside of the model. And then UniPy has got this kind of, it separated these into two things, where it was training this nice inverse dynamics model with taking states and it would unfold things. It does use another model to be able to eventually infer what the actions are for this model, and something that's more related to the robotics applications that they have in this paper.
Just use the IBM at the end to read the after dinner.
Yeah, they've got some, not even that small, but there's some video generation model that they're using before the IBM, and the IBM is being used for the action part. So now there's two separate models here, and really that's the question to kind of think about. Is it keeping these as two separate models, whether or not it's a good choice, trying to put them together in one model and train that from end to end. Yes.
Maybe Genie has some separate components. Like first you train like video implementer, and you also train this like IDM, and after this you separately train a dynamics model which given the video tokens and latent action difference. So it's like Genie does have separate components, but like the direction that you're getting these components are reversed. The original.
Mm-hmm. So then why do you think they might have thought about reversing these components, or what are some of the advantages of doing it that way?
So Genie doesn't have to rely on like action data, right? So you don't have to start from like kind of learn what an action recommendation and unsupervised way. Right.
Yeah, and that can be helpful. So, like, do you think that would lead to some easier generalization? Because like Genie is also trained over a bunch of different types of environments.
I think it's maybe complete the generalization, but you can have a model that's like less grounded, maybe like if you train like in this robotic scenario, maybe some of your latent actions are not like if you have like ground transactions where you like not seeing like directly relate to the real world, maybe you still need to have some component rate of like learning translations between your latent actions. Or people realizations.
Yeah, great. And that's one of the components for Genie that's becoming a bit more of interest to people lately, because this was trained on for a specific robotics model. So it had an IDM that worked for one type of robot. Here, Genie and the way it's trying to learn is now a latent action process, figuring out, okay, I mean, with some particular kind of boundaries on design, possible to maybe reuse now this way it's encoding this latent action process. Hopefully it can generalize some chunks of the IDM that are when it's training to possibly some other environments. At least something that might have some slightly different actions. Although I know we kind of discussed for a minute, at least for the first version of Genie, it's trained over a lot of stuff that are for platformer games. So maybe there are some different actions. It might be kind of like a superset of all the actions it considers, and every other data set is some subset of this. But here it's at least starting to get this process that could maybe generalize some other types of actions at least. Well, we could hope it'll fine tune a little bit faster. This ends up being kind of a weird concept. Often we think about the way things generalize in state space. That you can kind of like factor parts of the state and you don't have to worry about that. And like, do these concepts also apply to action spaces? Sort of like, at least there's not nearly as much work and understanding there in the way those could be factorized in a way that controls the dynamics and some other aspects. But I think that part is still sort of like in the study for what's going on in the community so far. And that's where we'll get to it a little bit later in the class. Yeah, there are obviously a couple of other like more foundational models for robotics. They kind of train some behavior clone process and then kind of like glue on something that decodes actions for the specific robot type. This is always going to be a bit of a challenge. Is where maybe it's a bit harder to find good foundational models that generalize for stuff that control things in the real world. Because even if you're doing video generation, there's a whole bunch of different things, they'll have different action spaces, and that becomes a harder thing to actually transfer to other problems later on. Great. Any other comments, questions? All right, let's take a break there for the next little bit. We're somewhat close. Yeah, okay. And we'll start up again at 2:28? Yeah, 2:28.
I have a question.
Yeah.
This thing I've been working on. So I don't know if you read the chapter paper.
Yeah,
Yeah.
a little bit.
I wanted to do that to robotics, just trying to like explore the ideas. And like basically the idea is to predict the next state in latent space and then decode the upper OS secret from it. I'm just using like a simple RoboMimic dataset for left hand. That's like my first task. So I get clip to encode my image plus my OSC for XYZ and the equipment.
That's OSC.
The operational space controls.
Okay.
It's just the XYZ
Okay.
my
Like end effect.
my end control. Yeah. And then I put in the predictor. And then my Y encoder, I'm supposed to get the next state and then encode it, and the loss is basically between the Y encoder's output and the output predictor. And they're both the same size. So basically I'm trying to train a latency. Now the problem in the Java paper, they only do images and videos. And what they do is they have the same size for the X encoder and Y encoder. So the way they update the Y encoder is through exponential moving averages. The reason they do that is to not have collapse. Because if you train accuracy without EMA, this would collapse. And I tried that, and it collapsed like first try. So my question is, here I want to do like, I don't want to do just one frame, I want to do like the next 5 frames. So the next 5 states. The problem when I do that, the Y encoder input, the whole architecture, the whole model would be much different than the X encoder, right? Even the output is the same, they have both output and latent space. Because they're different, how can I do something like EMA? And not, yeah.
Well, so you're using the JEPA concept here to, are you predicting part of the images or part of the plan?
Well, part of it, like, the whole point what I'm trying to do with the predictor is predict the next state and latent space, and then later decode the OSC with it, right? Because my thinking is like, if I can predict the latent space, I can easily like have a decoder after and like get the OSC. Just so I can do control.
Okay, I mean, that part makes sense. Just trying to, because JEPA is usually used because the model is given like segments of an image, it has to fill in the stuff that it's not given for the segments. So then how is this doing kind of like this filling in part?
I'm not doing the filling in part because the VJPO with the videos, it's not, it's more like video prediction of some sort. I'm just following Jan Lekman's like original JEPA idea paper, right? Where there's no concrete plan, it's just predicting latent space kind of thing. Would you think it's better if I have a more concrete plan of predicting the
Well, it's good, especially if you're investigating a new model type to figure out like, well, this is the data they'd want to see it be able to predict in some structured way. For even this, like you could have the mask out part of like some of the features in the OSC, you know, it should learn to be able to predict that. And then, so it'll have to have a good latent to be able to just, you know, to predict that stuff well. So I think that's part of what you might want to adjust. But said, you also said that you're having troubles getting this encoder to not collapse.
yeah.
Mhm.
They solved it by doing CMA, but the problem with my thing is that I feel like if I do just one frame here, it's not gonna get enough. So I do like 5 frames, 5 OSC. So it's like the input is 5 times the input here.
Mhm. That can be helpful. And this is a frame, this is like one of these images. that's being
Like just like a arm, like the arm. Just for I'm trying for the left right now, like the left task.
I mean, in terms of things for the collapse, you might just need to like lower, was it the momentum for this exponential moving average? So you can make this kind of move even slower.
But even if they're different, like they're different sizes. The JEPA, when they're the same size, it's the same weight, starting with the same weight. It's just the updating is like slower here. The problem is that because this is different size, I don't know how to handle that. Like, should I just do one image here and try it? Is that enough to think?
I would start with that. I could sort of like start with the simpler stuff and then build on that after it works. But it would be good to look into the way you're using JEPA, because it is sort of like, here's an input, some of the input is masked out, and still be able to predict the original input. So something about that might also help enforce that this doesn't end up collapsing so well, so it'll become a better encoder or decoder.